In this lesson, we're going to talk about the fundamental theorem of calculus. And the fundamental theorem of calculus is something you've really seen in the previous lessons. It's basically telling us that if we've got a continuous function that happens to be a derivative, so if f prime is continuous between a and b, then the definite integral of f prime is essentially the total change of the original function f. And that's essentially what we said in the last lesson. The integral of a rate of change is a total change. And so basically what we're looking for when we're thinking about computing definite integrals is looking for a function whose derivative is the function inside the integral sign. So let's see how this plays out in a couple examples. Okay, first of all, let's assume r prime is the rate of change of the value of your retirement account from time t measured in months. So how can we interpret the integral from 0 to 5 of r prime of t dt in light of the fundamental theorem? Very simply, we would need to find the function r rather than being the rate of change of the value of your retirement account. We want r to be the actual value of your retirement account. And we would compute that for time 5, we would compute that for time 0, and we would subtract. So basically, you're thinking about the value at the end of the time, period 0 to 5, and subtracting the value at the beginning to get the total change in value. That's all that the fundamental theorem basically says. If you're integrating a rate of change, you get a total change, and that's a pretty simple relationship. We've seen that with velocity and position. So let's look at a specific example with this investment account. Let's assume that the rate of change of your investment account is 120. So that's a constant rate of change. Every month you get $120 more put into your account, either through interest or dividend, or perhaps you're depositing. The rest of the account stays the same. And let's also assume that we've figured out a formula for the actual value. So the rate of change in your investment account is $120 per month. And the actual value of the account is 500 plus 120 times t. So that's the value of the account at any time t. So if we go back to our example and say, what would the total change in the value of the investment account be over the 5-month period? Fundamental theorem says, oh, that's simple. We integrate from 0 to 5 the rate of change of the retirement account. That should give us the total change. So we know from previous lessons that's total change in r of t from time 0 to time 5. And the fundamental theorem says the way you actually find that is if this was a rate of change, then we take the original function, the actual value, and here's a symbol that says evaluate from 0 to 5. That's just a fancy way of saying stick in 5 for t, then 0 for t, and then subtract. And since we actually have the function r of t, we can plug in 5 and get 500 plus 120 times 5 minus 500 plus 120 times 0. And that looks like 500 plus 600 minus 500, or $600 in total change in your retirement account from month 0 to month 5. Does that make sense? Well, in this example, if you go back to the rate of change, yeah, it actually makes a lot of sense. Every month you're putting in an extra $120, so over 5 months you would expect 120 times 5, you'd expect $600. So that's the change in your retirement account for the first 5 months. Okay. So let's look at another example that's a little meatier. Let's assume that the velocity of a baseball, t seconds after being hit by a baseball player, is given by 100 minus 4t. So you hit the baseball at time 0, it's going 100, we'll say feet per second, if you'd like, and then it slows down over time. And that the position, and we'll say this is in feet, t seconds after being hit is given by the 100t minus 2t squared. So according to the fundamental theorem, what is the integral from 0 to 2 of this velocity function v of t dt? Well, the first thing you want to do is realize that velocity is a rate of change. So we can think about velocity is really the derivative of position. We've talked about that before in previous units. In I think Unit 3 and Unit 4, we talked about velocity is the derivative of position. And so now we say, oh, here's an integral of a derivative. The fundamental theorem says, well, the answer should just be s of 2 minus s of 0. So the original function for position at time 2 minus the original function at time 0. And since we have that function, since I gave that to you, we just need to compute those. So 100 times 2 minus 2 times 2 squared minus 100 times 0 minus 2 times 0 squared. Yes, that's 0. That was silly to write out, but it's good to do everything out at least once. So it looks like 192 feet. Okay, so pretty straightforward. Fundamental theorem, if you're integrating a rate of change or a derivative, the answer is just the original function at the top limit minus the original function at the bottom limit. Okay, so let's look at one more example that's a little more complicated, and we'll go back to marginal cost, which we talked about in the derivative units. And so if you recall, C of Q is the cost of producing Q items, and then C prime of Q was the marginal cost, how much it would cost to produce one additional item or unit. So we can conclude a couple things. The cost of producing 0 units we'll call C of 0. That's a pretty straightforward application of what the function C of Q means. And you might think, well, it shouldn't cost you anything to produce nothing. But if you've got a factory, these are sometimes called fixed costs. So you need to rent the building, you might need insurance. Before you actually hire people and buy materials and actually start producing something, you have some fixed costs. So you need those costs to be paid regardless of how many items you're producing. And then there's this notion of variable cost. So the cost to increase production from A units to B units is essentially this integral. And let's think about that. If you think about marginal cost, the C prime of Q, that was the dollars it required to produce one additional item. So the units are essentially dollars per item. And if you think about the dq, q is the number of items, so that's times however many items. So if you just look at the units again, this is going to tell us how much it costs to go from A units or items to B units. So what's the additional cost of producing those extra units? And sometimes that's called the total variable cost. So the total variable cost to produce B units is the integral from 0 to B of C prime of Q dq. So you multiply the marginal cost, dollars per item, times the number of items. You basically add all of those up, and that's what the integral is doing. So one way to think about total cost of producing B units is your fixed cost, your building, your insurance, that's C0, and then your total variable cost, how much it costs to go from producing nothing to producing B items. So you can review this in the textbook if you like, but we'll just do an example to help make it clear. So a marginal cost curve is given below, so we'll think about this as being Q, the number of items produced, and we'll say that this is C prime of Q, and so this is dollars per item or dollars per unit over here. And these are going to be, these units are in thousands to keep things simple. So the 10 here means 10,000. Okay, so for fixed costs, and if you remember, that's essentially the cost of producing nothing. or $1,000. Costs us $1,000 to rent some space and get some insurance. And I want to know what's the total cost of producing 100 units. Well, the previous slide we said, okay, total cost is pretty easy. It's going to be your fixed plus the variable cost of going from 0 to 100 units. So in this situation, our fixed costs are the $1,000, and our variable costs are given by integrating the marginal cost. And so if we look at this, you might be thinking, well, now I'm in a little bit of trouble. We don't really know what this function is. All we have is a picture. The best we can do here is do some estimating, and there are a lot of methods you can use. We've done a whole bunch of different ways of estimating areas. You could use some rectangles. I might say, what if we used a couple rectangles here and use the right-hand sum? If we use 2 rectangles, that might be 50 units times, oh gosh, that looks like the 50 times the 7,500 for the area of the first rectangle, plus 50 times about 4,000 for the area of the second rectangle, which gives us 50 times 11,500, and that's 1,150,000 divided by 2. That should be about 575,000 if I'm doing that right. And that's a pretty good underestimate. Again, don't forget that was this underestimate here, using those 2 rectangles. If we wanted an overestimate, I'll let you fill out the details, but it should be 50 times about 13,000 plus 7,500. And I think if I computed that right, that's about 1,025,000. So a good estimate is probably somewhere in between, and I would say perhaps the total cost would be about 800,000. Now this is pretty rough, but I'm just picking something between the underestimate and the overestimate. Okay, so that's an example of marginal cost. What I'd like you to do is reflect and ask yourself if you can use the fundamental theorem to evaluate a definite integral, and can you apply fundamental theorem to marginal cost problems. Thanks for listening.